This is free response question number 4 from the 2024 AP Precalculus exam. It's about trigonometric, exponential, and logarithmic equations. If you appreciate the content, please give it a like. Pause the screen to read over these general instructions. Part A. The functions g and h are given by g of x equals e to the x plus 3, and h of x is equal to arcsine x over 2. A. Part 1. Solve g of x equals 10 for values of x in the domain of g. We need to set g of x equal to 10 and solve. I'm going to just space this out a little bit. Because to make the base e go away, we do the log base e on both sides, but of course log base e is ln. But remember that I had log base e because on the next step, the log base e and the base e will cancel each other out. But yes, log base e is better written as natural log. So the natural log and the base e will cancel each other out on the next step. But right now we are taking the natural log of both sides of this equation. So on the next step, we have x plus 3 on the left because, one more time, the log base e and the base e cancel each other out, leaving behind the x plus 3, equals natural log of 10 on the right-hand side. Getting the x by itself, we subtract 3 from both sides. So we have x is equal to the natural log of 10 minus 3. I'm going to go ahead and put the 10 in parentheses to make it really clear that the minus 3 is not included in there. And that's it. This is the answer to A, part 1. Or instead of putting parentheses, you can put the negative 3 in front to avoid ambiguity. B, part 2. Solve h of x equals pi over 4 for values of x in the domain of h. H of x is equal to arcsine x over 2. So h of x equals pi over 4 becomes arcsine x over 2 equals pi over 4. We can cancel out the arcsine on the left by taking the sine of both sides of the equation. Sine and arcsine are inverse functions, so they cancel each other out and leave x over 2 is equal to the sine of pi over 4. If you have not yet memorized these 9 trig facts, pause the video and memorize the chart right now. We have memorized that the sine of pi over 4 is radical 2 over 2, or 1 over radical 2. So making that substitution, we have x over 2 is equal to radical 2 over 2. Multiplying both sides of the equation by 2, the 2's in the denominator will cancel out. So we are left with x is equal to radical 2. And that's it. This is the answer to A, part 2. Part B. The functions j and k are given by j of x is equal to this expression, and k of x is equal to this expression. B, part 1. Rewrite j of x as a single logarithm base 10 without negative exponents in any part of the expression. Your result should be of the form log base 10 of expression. To solve this problem, we will be using one or more of these 4 log rules. If you need to, pause the video and add these to your notes. This purple rule tells us that if we have a factor multiplying a logarithm, you can move that factor to the exponent. I'm going to apply that rule with this 9 right here, and I'm going to move it to the exponent. Next, I'm going to use a combination of the product rule and the quotient rule. Quick side lesson: if you have a sum or difference of 2 or more logs with the same base, you can rewrite that expression as a single log in one step. The presence of even one minus sign tells us that there will be a fraction involved. So we know we're going to have the log of some quotient. After that, a positive term will give you a factor in the numerator, and a negative term will result in a factor in the denominator. Because this first term is positive, the a will end up in the numerator. Because the second term is negative, the b will end up in the denominator. Because the third term is positive, the c will end up in the numerator. And because the fourth term is negative, the d will end up in the denominator. I can write this long purple expression as a single log base 10. The presence of this minus sign tells me it will be the log of a quotient, so I'm going to go ahead and put a fraction bar. This first term is positive, so the factor of 8x to the 5th power will be put in the numerator. The second term is also positive, so I will have times 2x squared also in the numerator. The third term is negative, so the x to the 9th power will end up in the denominator. I can easily simplify this more. J of x is equal to the log base 10 of. 8 times 2 is 16. When you multiply with like bases, you add the exponents. So 16x to the 7th power over my x to the 9th power. Let's simplify a little bit more. J of x is equal to the log base 10 of, I'm going to bring down the 16 because this part is now going to simplify. Normally, when I divide two factors with like bases, I subtract the exponents, but that would give me 16x to the negative 2 power. We were told that we should not have any negative exponents in any part of the expression. So instead of doing that, let's leave the x to the 2nd power in the denominator. J of x is equal to log base 10 of 16 over x squared. You can go directly to this answer and avoid the business about x to the negative 2 power by thinking of it this way. We have 7 x's in the numerator and 9 x's in the denominator. The 7 x's in the numerator will cancel out 7 of the x's in the denominator, leaving behind 2 x's in the denominator. Small mistake in the directions. This should say a single logarithm base 10. It shouldn't say natural logarithm because that would be base e, not base 10. Small mistake. B part 2. Rewrite k of x as a single term involving tangent x. We need to rewrite this expression as a single term involving tangent x. This is going to require knowledge of a few identities. Here are a bunch of identities that I would like you to memorize. Pause the screen and write these down. However, these are not all created equally. I think the set of blue identities are sort of the most important. They show up the most often in various problems. In addition, make sure you know these basic trigonometric identities as well. For the problem we are working on right now, I think we are about to use this identity, so pay special attention. The identity we use the most often is the one that goes like this: sine squared x plus cosine squared x is equal to 1. If we subtract sine squared from both sides, we get cosine squared x is equal to 1 minus sine squared. This is exactly what we see right here. So we can substitute cosine squared x for 1 minus sine squared. The expression inside the parentheses then becomes cosine squared x over sine x. However, there is a substitution that we can make for secant x as well. We have memorized that secant x is equal to 1 over cosine x. It is often helpful to rewrite things in terms of sine and or cosine. So let's try replacing secant x with 1 over cosine x. Replacing secant x with 1 over cosine x gives us k of x is equal to cosine squared x over sine x times 1 over cosine x. Notice that we have 2 factors of cosine x in the numerator and 1 factor of cosine x in the denominator. So the 1 factor of cosine x will cancel out one of these 2 factors of cosine x in the numerator, leaving behind a single cosine x in the numerator. I'm going to erase this in a moment. I just want to be extra clear. Cosine squared x means cosine x times cosine x. So this is what I meant. Cosine x in the denominator will cancel out one of these 2 cosines from the numerator, leaving behind just cosine x over sine x. Cosine x over sine x. That sounds familiar. That's another one of our basic identities. Cosine x over sine x is equal to cotangent x. Except, we are supposed to write k of x as a single term involving tangent x, not cotangent. So what is the relationship between tangent x and cotangent x? Tangent x and cotangent x are reciprocals of each other. So tangent x is equal to 1 over cotangent x, or cotangent x is equal to 1 over tangent x. It's the second one that we need. In fact, replacing cotangent x with 1 over tangent x gives us the final answer. K of x equals 1 over tangent x, a single term involving tangent x. Part C. Function m is given by m of x equals arc cosine of tangent 2x. Find all values in the domain of m that yield an output value of 0. Finding values in the domain of m that yield an output value of 0 means setting m of x equal to 0 and solving. So we need to solve the equation arc cosine of tangent 2x is equal to 0. By the way, cosine with a -1 superscript means the exact same thing as arc cosine written this way. So whenever I see this, I'm going to just say arc cosine, and it means the exact same thing as this. If you're more comfortable with arc cosine written this way, it's okay to go ahead and replace cosine with a -1 superscript with this expression instead. Arc cosine and cosine are inverse functions, so you can sort of cancel out arc cosine by taking the cosine of both sides of this equation. So the cosine and the arc cosine cancel each other out, and we end up with tangent 2x on the left-hand side is equal to cosine of 0 on the right-hand side. If you have not yet memorized the restrictions on the values of arcsine, arc cosine, and arctangent, pause the video and add this to your notes right now. Arc cosine is only allowed to be between 0 and pi. I'm not sure if this restriction is going to matter on this problem, but let's keep it in mind. Here's a unit circle. 0 is right here on the unit circle, and cosine is the x value on the unit circle. The radius is 1, so this is the point 1, 0, and cosine is the x value. So the cosine of 0 is 1. So making that substitution, we have the tangent of 2x is equal to 1. Next, I would like to solve for the expression inside of the tangent function. I want to solve for 2x, and I'm going to start by finding the reference angle by asking myself the tangent of what angle will equal 1. We have memorized that the tangent of pi over 4 is equal to 1, so pi over 4 is the reference angle. By the way, reference angle means the angle between the terminal side and the nearest part of the x-axis, like this. On the interval from 0 to 2 pi, these are the four angles with a reference angle of pi over 4. 2x has to be one or more of these. However, we also know that tangent has to equal positive 1 specifically, not negative 1. Tangent is the slope on a circle, so we need to restrict ourselves to the angles that have a positive slope. So we can forget about the second quadrant and the fourth quadrant where the slope would be negative. So 2x has to be one of these angles, or it could be either. The angle in the first quadrant with a reference angle of pi over 4 is pi over 4 itself. So 2x could equal that. Or the angle in the third quadrant with a reference angle of pi over 4, what's that? We can think of pi as 4 pi over 4. Therefore, this angle in the third quadrant must be 5 pi over 4. It's pi over 4 past 4 pi over 4. So that's the other possible value for 2x. 2x could be pi over 4 or 5 pi over 4. Here's where it gets a little bit tricky. We just found two possible values for 2x on the interval from 0 to 2 pi. However, we are supposed to find all values in the domain of m. And the domain of m is really unlimited. So there are infinitely many values. We found 2 so far. But when you have solutions that are separated by a semicircle, they are separated by pi radians, you have this situation where every time you add pi, you get another solution. So, for example, starting in the first quadrant with pi over 4, if we do pi over 4 plus pi, we get 5 pi over 4. That's another solution. However, if we add pi again, that's going to take us back to this position. Let's see what that would be called. As I'm adding pi, I'm going to think of it as 4 pi over 4. So that would be 9 pi over 4. So if I went all the way around and back, this would now be called 9 pi over 4. But if I add pi again, I'm going to get another solution. If I add pi again, I'm going to get another and another and another. We can express that 2x is equal to infinitely many values by starting with the first value in the first quadrant, pi over 4, and adding multiples of pi. So I'm going to add pi k, where k is any integer. Now we have an expression for the infinitely many values of 2x. We still need to get x by itself by dividing both sides by 2. How do you divide pi over 4 by 2? Well, the shortcut is the 2 ends up in the denominator like this. It's going to end up as pi over 8. If you don't like that little shortcut, pi over 4 divided by 2 is the same thing as pi over 4 times 1/2. In this form, it's a little bit easier to see why the answer is pi over 8. Of course, pi k divided by 2 is simply pi k over 2. Or, if you wanted to, you could write it as pi over 2k, which is the same thing. For the final answer, we say x equals pi over 8 plus pi over 2k, where k is any integer. Make sure you include this phrasing. Before I end this video, I want to do a quick side lesson showing how the problem would have turned out if it had been sine or cosine instead of tangent. We would solve for the 2x inside as before by first determining the reference angle, by asking the sine of what is 1/2. We have memorized that the sine of pi over 6 is 1/2, so in this case pi over 6 would be the reference angle. On the interval from 0 to 2 pi, Here are the 4 angles with a reference angle of pi over 6. However, we want sine to equal positive 1/2, and sine is the y value on the unit circle. So we will stick to quadrants 1 and 2, where the y value and thus the sine function is positive. The angle in the first quadrant with a reference angle of pi over 6 is pi over 6 itself. What about this angle in the second quadrant? Well, we can think of pi as 6 pi over 6, so this angle in the second quadrant must be 5 pi over 6. So, on the interval from 0 to 2 pi, the two possible values for 2x are pi over 6 or 5 pi over 6. However, we have no such limitations. We are not restricted to the interval from 0 to 2 pi. How do we turn this into infinitely many solutions? This is different from the tangent situation where the two solutions were separated by pi radians. In that case, we were adding multiples of pi, which would always take us to another solution. Because these two solutions are not separated by a semicircle, they are not pi apart, adding pi will not take us from one solution to the next. Therefore, we have to write these separately, and we will turn each one of these into infinitely many solutions by adding multiples of 2 pi. Going all the way around and back to here will give me another solution. Adding multiples of 2 pi will give me infinitely many solutions that land in the first quadrant. Similarly, adding multiples of 2 pi to 5 pi over 6 will take us all the way around and back to this same position in the second quadrant. So we can get infinitely many solutions in the second quadrant by taking 5 pi over 6 and adding multiples of 2 pi like this. Finally, we get x by itself by dividing both sides by 2, but we have these two different expressions that we just keep separate. So we end up with x is equal to pi over 12. Remember, when you divide this fraction by 2, it ends up in the denominator and you get the 12. So we have pi over 12 plus. When you divide 2 pi k by 2, the 2 cancels out. So you would end up with pi k right here. And then you would have or. Dividing by 2 here will give you 5 pi over 12. And dividing by 2 here cancels this out, and you have pi k. So this is what your solution would look like if it had been sine, and cosine would work similar to this. The point is you would have two separate expressions instead of just one. We should still say where k is any integer. What I just showed you about adding multiples of 2 pi instead of the special case of adding multiples of pi, it always works to add multiples of 2 pi and keep the answers separate. So right here, back with the tangent, when we had 2x is equal to pi over 4 or 5 pi over 4, the two solutions that you would have on the interval from 0 to 2 pi, we could have turned this into infinitely many solutions by adding multiples of 2 pi right here. So right here I could say pi over 4 plus 2 pi k, or 5 pi over 4 plus 2 pi k. I did not have to simplify this down to just pi over 4 and then multiples of pi. It's equally valid to keep these separate, and if you do it this way, you always add 2 pi k. This always works. And then on the next step, we would divide both sides by 2. So here comes another valid version of the answer instead of this. We could have written, let's see, pi over 4 divided by 2 is still pi over 8. And then dividing this by 2 will leave pi k. Or dividing this by 2 we will have 5 pi over 8. And dividing this by 2 leaves us with pi k. So as long as we still include the phrase where k is any integer, this is another valid version of the answer. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.